Hi, today we will talk about a model in which we will talk about a comparative study regarding NASA's spacecraft. The NASA's Aeronautics and Space Administration, National Aeronautics and Space Administration NASA, its module for the spacecraft, and we will discuss various electrical power related issues in the NASA's spacecraft, and we will compare it with the Earth-based smart grid power distribution, energy distribution network, and how it differs, and what are the research gaps in academia and industry. We will focus not only spacecraft. In future we will talk about the commercial aircrafts and military aircraft. For this presentation we will talk about physics informed neural network model predictive control for NASA's aircraft, NASA's spacecraft, and we will talk about how to control, how to optimize, how to forecast various issues, and how to detect the errors in the spacecraft flight of the NASA. So let's begin our journey now, and we will talk about this model that I designed. It's a model implementation for NASA's future space aircraft. So in this, I took references from US Air Force Research Labs papers, documents, which is listed here. Then I took some references from IESO's and Ontario's smart grid reports. These are recent reports in last 3 to 4 years. Ontario Energy Board, because the electrical power system is related with the earth-based systems, and the model I designed is for earth-based and the NASA's spacecraft. Then I took help from IEEE's research paper. These are some of the information here, that which papers I took help from. So you can have a look at this, and let's discuss them in shortly. And the NASA's and Canadian Space Agency's papers, Boeing's, Airbus technical documents. These are also recent documents that I took help from. And then there are many issues related to the aviation, related to space, spacecraft, related to Airbus, Boeing, NASA, Canadian Space Agency. So here I discussed those issues, research gaps, and how these research gaps are being addressed partially in my model. Some of the academic gaps, we will talk about those academic gaps, that which academic gaps we had, and we will talk more in detail about those issues as well. And then for our model and for our research, it has two components. One is the software related and another is the hardware related. So in this video I'll discuss about software model, and in another video I will present about the hardware implementation of this model. So this is a comparative study of smart grids and the space systems, spacecrafts, UAVs, and the aircrafts. And in our hardware implementation we did some work as well. We will continue talking about hardware and software related issues. So it's a comparative implementation of unified physics informed neural networks and model predictive control. So we will talk about those in detail here, and how we design the algorithm, and how we are going to implement it in hardware. So hardware section is in another video. So when we talk about smart grids on Earth based, we talk about the applications for intelligent load control, forecasting, and optimization for the NASA's, and for the future aircraft. We talk about autonomous physics informed neural network and model predictive deployment for deep space energy systems. So for the power systems on Earth, they operate under dynamic load patterns, because those load patterns are dynamic, and these include, because it includes almost everything present on Earth, right? Residential, commercial, and industrial. Whereas when we talk about a spacecraft, they are self-contained and must operate without real-time human intervention, because humans are not there, especially for UAVs and for the spacecraft. So it means whatever has to be done, it has to be done automatically. Either it's some optimization, forecasting, error detection, some actuators are to be moved, some action has to be taken to balance the energy, to optimize the power and energy, to better distribute it, load shiftings and everything. This has to be done automatically. So that requires predictive physics aware power management to handle temperature shifts, power surge, and limited solar exposure, because there are so many parameters in these, especially for the spacecrafts, that has to be addressed, which are not as simple as we have on the Earth. So for the Earth, for smart grids, that is to make sure that the smart system on the Earth should be reliable, supply voltage regulations, fault resilience, and high efficiency. Whereas in this case, as we talk about our project, our model will handle temperature shifts, power surges, limited solar exposure, and subsystem priorities like communications and navigation and propulsion, which is related to the avionics. Now, the electrical related challenges we will talk about, and we will do a comparison of the electrical related challenges that we face and how they are addressed in our model. So let's talk about it. For the smart grid, voltage sag and harmonics from non-linear loads, that is a challenge. And the distributed energy resources like solar introduce unpredictability, because whenever we combine the various sources of renewable energy into one grid system, so there are so many issues. Whereas if we compare this with the NASA's spacecraft, solar power variations are there, which are due to orbital position, because for the spacecraft, its orbital positions, its maneuvering, its movements, they differ, and it means uh, the sunlight that is coming to the solar panel for the NASA's aircraft, it is not always constant. It changes because of the direction, changes in the directions and movements. Then the electromagnetic interference, EMI, and component degradation, that is also an issue, because when it is in atmosphere and then in space, there are issues with the electromagnetic interferences. Then the spacecraft that has to go through high thermal stress and radiation induced in circuit faults. So it means some faults are actually physical faults, because the system is not stable, it is moving every second, and it's changing the direction, it's changing the speed, and the overall environment from the atmosphere to space is changing. So the our proposed artificial intelligence based framework that we proposed, if we compare that with the smart grid, our physics informed neural network learns to respect power laws, while forecasting demand and managing voltage profile. Because in many research papers, this issue has been addressed, that is related to Earth, but the comparison or the correlation between the spacecraft and smart grid. This is our innovation that we are addressing, and we are trying to design same model and train it here on the Earth, and we can implement it into a spacecraft. Like this is the one of the contributions for the NASA aircraft's physics informed neural networks model electrical and thermal behaviors of power buses and the batteries, whereas the MPC model predictive control ensures time ahead scheduling of heating, thrusters, and battery charging while respecting hardware limits. Because if the system in the spacecraft or in the aeronautics or commercial aircraft, if that is not followed, the physics, the structure, the thermal effects, and all of those, if that is not properly handled in case of spacecraft and the aviation, it means there are issues like that. We can we have to see the specifications, the threshold, the power consumption, power distribution, and working functions of the various devices and components in the electrical system in the spacecraft. So the architecture overview of our model is like for the space grid, and I'm comparing it with the NASA's spacecraft. In the space smart grid, we do with hardware with the SCADA enabled RTU, the smart meters and edge processors. Jetson Nano as well, that I implemented Jetson Nano later in my hardware implementation that I will discuss in another video. So for the NASA, the software which are used, which are common, which are very improved software. That one is the Basilisk, and then the Open MDAO. These libraries are being embedded in my algorithm, and I use this through Python. And for the hardware side, Jetson Nano STM32 controllers, thermal electric feedback loops. I mean, for the hardware that I will explain later, there are many components and units for computing, and then for the for my AI model that requires lots of computing and implementation, and then it moves on and gives directions to the actuator to work. Now, let's do for the power optimization strategy that we used in our model, which is very important to discuss here. What power strategy has optimization strategy has been used. Like now, I'll compare again with the smart grid. Our model for the smart grid optimizes transformer and feeder operations. So the power equation is here, and that ensures voltage is stable across distributed line. Whereas in NASA's spacecraft, our model manages energy from solar panel, and we follow this universal formula for the power. So this regulates supply to propulsion and avionics system. For the MPC objective in our model, the smart grid for the smart grid that maintains grid stability by adjusting load flow. So if you adjust the load flow, that will take care of the grid stability. Whereas in spacecraft, the model ensures onboard systems stay within thermal safety, because thermal objectives, thermal considerations, and the atmospheric or space related environment considerations are very important. That makes the model different. Then for the MPC calculations, these are my calculations here. Smart grid maintains voltage and current stability through load flow optimization, and this is the equations is used, and I have defined all the voltage at the bus, and then the reference voltage, then the current drawn at particular time, and then and a weighting factor that we have to embed here, a weighting factor. In the neural networks in deep learning, this weighting factor is induced, and this is related to the physics and the formation and the continuity of the model. Whereas for the NASA spacecraft, that ensures safe operations of thermal sensitive systems through thermal control and load shifting. Why I talk all the time about thermal, not only thermal related to solar, but also because the temperature either less or more, that actually creates an impact for the devices to work. So we have to consider these equations for the temperature. Like the what I did it in my model is like I did some kind of calculation for the cost function. Like for the smart grid, purpose is to penalize voltage deviations, whereas here the cost function keeps subsystem in a safe thermal range. In a smart grid, it minimizes I square R losses by discouraging high current, whereas in this case, in the spacecraft, it penalizes unnecessary or risky power redistribution as well, because redistribution is another issue in the spacecraft and aeronautics. So the spacecraft dynamically prioritize power across subsystems under changing solar exposure or mission phase, because the environment is different, the radiance from the sun is different, and its intensity is different. So it means there is a possibility of the redistribution. Whereas in a smart grid, that enables our modelist enables a smart grid to predictively adjust transformer taps like NDR, their usage, or capacitor banks. So this is again the terms we have used in our presentation. All terms are here, so which are being discussed here. So these are some of the terms that we discussed in our model. The voltage at time k, then the V reference is the target voltage, and the formula is there. And but this is not just here. What eventually we did is, like, we calculated various losses in the data or in the physics informed neural network, then the losses actual then the losses in the boundaries that we composed, and the third is the losses in the data, that actual data that is we are getting. So the two datas are already available. One is the physics informed, another is the data for the boundaries, whereas the third data is coming from the sensors as it goes. So we have to make sure that for our predictive model, our model predictive control, we have to make sure that it is following the MPC control. So for the smart grid, the this forecast derived from smart meter inputs, time of the day. I mean, this is the data I'm talking about, load forecasting. Time of the day, weather, and seasonality drive proactive load balancing that contains time, temperature, solar irradiance, and past usage. Whereas when we talk about spacecrafts, that we talk about forecasting load for life support, heating, telemetry based on mission scheduled and orbital environments. So then our parameters are a bit different. In addition to the one we discussed in the smart grid, we have to take care of the orbital position, system cycles, and the thermal load. So then we will talk about the forecasting inputs in our model, how these forecasting inputs are being discussed in our model. So this is also very important to discuss all these as well. So for this particular thing, we will talk about weather APIs and past demand data for the smart grid, and EV integration and battery levels. Whereas in NASA spacecraft, thermal subsystems duty cycle we talk about, solar incidence predictions, because we have to know we have to forecast the solar incidence, and we have to predict, okay, at this level, at this altitude, at this pressure level in the atmosphere, or at this position in the orbital position in the space, our solar incidence would be this. And then if this would be our solar incidence, what would be the result? Then in spacecrafts, we have to talk about altitude control influence on the solar gain, because uh, as much higher the spacecraft goes, much higher means further away from the Earth. So it means that is kind of a distance from the Earth. So the altitude control influence on solar gain. So we have to go through a very different science for this. Then we talk about temporal modeling for both A and B. When I say both A and B, it means A is for the smart grid and B is uh, for the NASA system. So we will talk about that in detail here. And in the video, you must be watching some of the documentary from the NASA that is related to the electrical systems as well. So I will just try to make the slide more obvious for you to read what I'm talking about, and we're trying to fix it, the window. Okay, now for the temporal modeling, as we discussed here, the time evolution of system state and control input. Then we have this equation where state vector at a certain step k, for example, we are talking about voltage or state of charge or temperature for any variable. So state vector at certain step k. I'm not saying at certain time k, at step k. So then the control vector at step k. So there are two. One is the state vector. That this is the state of the vector, and what is my control vector, especially for the MPC. So this models how future conditions depend on current state and input. Uh, for the stable distribution of loads in our model for the smart grid, actually, uh, this is achieved by adjusting feeder loading and transformer tab settings based on priority and the location. and the equation is like the total power is the power, the total voltage and the current. I mean, you just multiply it. Whereas the load shedding is like we have to consider the voltage and the current again. So either the minimum voltage is more than at certain instant of time or step, or the at that particular time on instant if the current is higher than the maximum current. So that is the like for the stable distribution of loads. Whereas in NASA spacecraft, critical subsystems like communications and thermal control prioritized using power budget tables as well. There is a power budget table so we have to see the power allocation, and that's what power we are getting from solar and from the battery, and we take that power loss from this, so it means this is the total power. So it's a bit different in case of spacecraft. Whereas if we talk about stable distribution of loads for the smart grid, stable load distribution objective is to ensure balanced and efficient power for across multiple nodes in the distribution system network. Whereas in NASA's spacecraft, we talk about a different scenario. We talk about let me just have a look because I can't see the slide. Let me make it more readable. Uh, for the NASA stable subsystem power allocation. So objective is to distribute available electrical energy among critical space subsystems, because that word available, electricity is very important, because the electrical energy is very important while avoiding overload or battery depletion, because there are chances of overloading and battery depletion as well. So the energy allocation formula, as I said, the total allocated power will be the sum of the solar and the battery, but while subtracting the power loss. So this is what we have here. And now for stable distribution of loads, if a in the smart grid, if a load at any node V1 at any node that drops below a minimum threshold or current exceeds safe limits I max, so it means that there is we have to take care of that. Whereas because I'm not having the symbols here in my model, because that has to be from the PDF symbols, I couldn't fix it here. So for the subsystem prioritization in the space, high priority, medium priority, and lowest priority, we do sections like for our highest priority in the spacecraft is the thermal control communication life support, which is very important. And for the medium priority is the scientific payloads, which I mean, if you have some actuators, you have some components, their payloads. And the lowest priority is for the storage and secondary communication, which are not vital, which are not essential. So for the control system checks, battery charge threshold uh, is not exceeded in our model. Load shift avoids thermal spikes, because in this model the load shift will avoid thermal spikes. If there is a change in the heat, so the load shift should not be affected. Whereas scheduling avoids the subsystem conflict. As I said, there is a subsystem conflict like redistribution, so schedule should avoid it. Whereas the methods to achieve load stability in a smart grid is to reconfigure figures and switch capacitor banks. So this is a strategy there. Whereas in a smart grid that uses DER to support local load. So there is an option of having the DER there. So the load priority logic, some consumers curtail before others. Like for some of the consumers, they are curtailing before the others. So the load priority distribution is different. And this is what I'm trying to classify the load distribution patterns or the priorities in both systems. So let me just go to the next slide here, and I have to make sure that that you guys are watching properly the video and the slides that I'm trying to show. Sometimes it goes on and off, so that's why I have to check it. Now, let's talk about this now. For the step 3 is stable distribution of loads. Why it matters? Because unstable load distribution in the smart grid that leads to transformer overheating or the line losses, I square R losses, or the voltage dips and the flickers, especially when we talk about during the peak hours, usually in the evenings, uh, or for the industrial loads. Whereas in space, energy is scarce and time sensitivity. Because time is very important, the energy is also very sensitive to the time. So no real repair if load crashes a critical system. If there is a critical system and the load is more than what was expected, so there is no real time repair. Whereas in earth system we still can manually go and repair, or automatically can repair, we do a repair here, but over there is no reach. So either uh, it means that we have to have some optimized system, some forecasting ahead of time. So in spacecraft, solar availability changes rapidly during eclipse phase. Whenever there is an eclipse phase, so the solar availability changes. Eclipse phase is what? Like if you are going towards or away from the sunlight. So systems, or when there is something between, some object between the spacecraft and the sunlight. So if there is an obstacle, let's say some other celestial object. So the in spacecraft systems must gracefully degrade under power stress. So whenever there is a power stress, so degradation is there, but it has to be gracefully. I mean, it should not uh, be degraded at once. I mean, there has to be a pattern of degradation. So the load priority control in our model for the smart grid, uh, it implements demand response tiers. Like let's say it's for the essentials, we have a different pattern for the hospitals, and for EV charging, which is another, if or if not a priority, which is a partial curtailment, whereas flexible is high voltage AC, that is deferable, we can defer it for some time. But the essentials are the hospital. Now, whatever priorities for the NASA spacecraft, power routing by subsystem risk, it means thermal loop should be greater than the life support, and it should be greater than the communication, and that should be greater than experiments. So it means our experiments are not as important as the communication, and communication is not as important as the life support, and life support is not as important as the thermal loop. So there is a priority score that we talk about: temperature, time, and the subsystem. Now, time ahead decisions in our model. So for the smart grid, that you utilize 24-hour ahead prediction to predict adjust transformer loading and battery dispatch. So you have like a time frame that in our smart grid at Earth that utilizes 24-hour ahead prediction. Whereas for the NASA spacecraft that predicts orbital eclipse shadow duration to be cool modules or pre-charged batteries. Like if there are like when I talk about pre-cooled module, it means there are some components, some hardware, some software, some optimization which are not run as the others are vitals are ruling, are flowing, as are working. So so this in this module, the the module predicts orbital eclipse or the shadow duration to pre-cool module or pre-charge batteries. So there are some batteries which are already charged, or there are pre-cool modules which are available. So if you predict the orbital eclipse or shadow, that after certain passage of time or the flight of the spacecraft, you will have a shadow coming, a celestial object, or some issues with the radiance of the sunlight. So it will predict and will let the pre-charged batteries to get ready and work. So the forecast equation for this model would be this, where WK is the disturbance estimate or model uncertainty, because this factor we have to include, that we included here in our model, WK factor, because if you see it has been added at the end of the equation. So we will see what those are. So for the smart grid, battery state of charge managed dynamically, like you have to manage the battery dynamically, whereas in NASA's high efficiencies with radiation tolerance and thermal constraints are considered, and we have to make sure that the battery is power should follow the physical laws as well, with priority given to charging during sun exposure. As soon as it is exposed to sun, it should start charging them. Has to be an automatic system. So for the smart grid, physics informed neural network encodes physical equations of grid, which are like Ohm's law, Kirchhoff's laws, and as soft constraints in the training. Whereas in the NASA spacecraft, physics informed neural networks that integrate solar incidence, thermal flux, and system dynamics in loss function. Why I talk about loss function? Because this is the purpose of our model design, where we talk about the total loss of the data. I mean, whatever data is available in real time, how far we are. Loss actually is telling us how far we are from the predicted or the desired output, desired target. And if we add that loss with the physics loss, because the physics related target points we have already set, so how far we are from, what are the losses, how far we are from those predicted results. And if we add that to the boundaries, so we will specify the boundary that it within that particular minimum and maximum range, our all model is exists that exists. And we have to make sure to control these three. This is actually the main uh, essence of the model, that is the total loss should be divided, or should be composed of three kinds of losses. One is the data loss, another is the physics loss, and third is the boundary loss. So if we can minimize this loss, it means we are almost near to the target. So if we talk about physics encoding example for the model, we have the equation here, and for the spacecraft heat transfer, we have the equation there, where in the heat transfer, Q is the internal heat source and alpha is the thermal diffusivity. So if you see the equation, we added the internal heat factor here, right, in the heat source, and alpha is the thermal diffusibility. If this is the heat source, and it means we have to include the diffusibility, and we have to see the change in the temperature, that how that heat has been diffused within the system, that is from the environment or from within the system, and the heat source. So for the sensor physics integration in our model smart grid, sensors report voltage current, uh, what we are getting from the sensors in the smart grid: voltage, current, frequency, harmonics, sensor noise. So in this, we take care of this with the Kalman filtering, which has this formula available, universal formula. And in the radiation hardened IMUs in the spacecraft thermistors, voltage sensors, processed via edge AI with sampling buffer. So this is like in our model, what we will take care of this, that this radiation hardened IMU thermistors are there, which has their own physics. So we have to take care of that physics and the voltage sensors. And we how we process that data, the physics informed neural network, we process via edge artificial intelligence with sampling buffer, that I have mentioned in my hardware component. Now, on step 6 is sensor physics integration in our model. For the smart grid physics based sensors data processing goals. So let me make it more readable, make it a bit larger. And okay, now I can see it. So step 6 is sensor physics integration in our model. For the smart grid physics based sensor data processing goals, one is like it maintains accurate real time monitoring of electrical parameters like voltage, current, frequency, power factor, and harmonics distortion. Whereas in the NASA space sensor physics and reliability goal, we have to make sure this model ensures accurate monitoring of thermal, electrical, and mechanical conditions, because we are not dealing only with the electrical parameters. In the spacecraft, as well as the smart grids as well, but here, because it is moving and going through various different environments. So the model ensures accurate monitoring of thermal, electrical, and mechanical conditions on board, especially under radiation and microgravity effects. Whenever there are like radiation effects or microgravity effects, when it goes close to a celestial object that has some gravity, as the Earth has some gravity, so there is a possibility of that our spacecraft will be pulled by those gravitational forces in the celestial objects present in the space. Common sensors in the space and in the smart grid. For the smart grid, the common sensors are voltage and the current transformers, phasor measurement units, PMUs, smart meters, power quality analyzers. Whereas in case of spacecraft, we have thermistors, RTD for temperature, and inertial measurement units. When we talk about inertial measurement units, it means we are talking about orientation and motion. We have to make sure that the magnetic field of the Earth, magnetic field of some of the other celestial objects or planets or satellites. So and our location, our orientation within the space. So we need inertial measurement units. And for the voltage and current sensors for bus power, of course, it is not as simple as we have in smart in the Earth-based systems. Then we talk about photodiodes, sun sensors for attitude and solar exposure. So it means photodiodes and sun sensors should be embedded there, and we have to take care of those. So what challenges we have in a smart grid? So let me make sure that I'm right there. Okay, so the challenges here, I forgot to add the title. So we will talk about the challenges, and we will make sure how we handle those challenges in our system, in our uh, uh, model, in our module as well. So we have to talk about it and see what challenges are there. One is the voltage fluctuations, like we are talking about smart grid, from the variable demand, that is the voltage fluctuations. Another in the smart grid is the renewable intermittency, solar, wind, and unpredictability. Because as I said, this is a DER, distributed energy resources are there, so there's a renewable intermittency in solar and wind. So now in challenges in space, I will do it one by one. Challenges in the space is radiation interference. As I said before, there's radiations from the sun, or and later on we'll talk about some of the thermal effects, thermal radiations as well. Then another is a single event upset. Let's say if there something happens all of a sudden, and then its repercussions are there, its effects are there, which has to be minimized or taken care of. Then extreme temperature cycling is there. Whenever there is extreme temperature, so it means that you have to cool down your system somehow to make sure, because in that cycling, that extreme temperature cycling is not linear. It's not like after certain distance we will have uh, this much temperature, and at certain height this much temperature, because it varies all the time. So then the delayed communication with the earth, and if we are doing it, we are trying to control some of the parameters, some movement or some other electrical related or electronics related communication or controls we are doing from earth, so there is a delay. So that has to be taken care of. Then how we do it in the smart grid, the solution is sensor plus the estimator plus real time filtering. That we discuss here in our model. Sensors plus estimators plus real time filtering. Then when something is being sensed, then we estimate uh, those inputs, and we merge it with our model, and then we do some kind of filtering. We start doing actions. So in smart meters and PMUs data buffered at edge controllers in our model. We have an edge controller where in the smart meters and PMU data is buffered. And the physics informed neural network based estimators corrects for noisy or delayed readings. If there is noisy or delayed reading, our physics informed neural network will take care of that. Whereas when we talk about solutions in here, we talk about sensor plus buffer plus AI pre-processing, because AI pre-processing is another additional thing, because the data, the availability of various parameters, effects, environment conditions, the AI pre-processing is very important. This has to be done in fractions of seconds. So the sensors value buffered in short time windows, that we have to take care that in short particular time we have to see the sensor values which are buffered like that at each micro picoseconds. Artificial intelligence filters anomalies using onboard trained neural estimators. It means when I say onboard trained neural estimator, it means some our model is more related with doing it and doing a training with the on the earth and then putting it into the actual situation. But AI filters anomalies using onboard trained neural and neural estimators. If we do this neural estimators during the flight, during the motion of the spacecraft, then we start training it over there because next mode of the model should be to train it in a real situation. Then the data compressed and relayed only when stable. So it means that the data is being relayed, compressed and relayed only when stable, because if the data is not stable, we cannot relay or compress. Now, step number 6 is sensor physics integration in our model. So these sensors are in the smart grid are susceptible to three things, so many things, but three things I'm talking about here: measurement noise, communication delays, and sensor drift. So we need to have some filtering situation and estimation technique which is solved with this equation. Whereas for in the spacecraft, edge AI models is like predict plus validate the sensors output. It is not just like taking the input and let it go. So it means you have to validate, we have to process the edge AI model, whatever is has been predicted. So instead of direct filtering like Kalman's, as we do in the smart grid, Kalman's filtering models. So this physics equation, which are again from various research papers and from the books that I took, and I mentioned it here, and we will see what those equations are. For the filtering and estimation technique in the smart grid, this is the Kalman's filter update equation, where estimated state at time step k has been discussed, with that we have to calculate the estimated state at time step k, which is here, and then the previous state, because if you are at, let's say, stage number 3, it means previous stage is state is step number 2. So it means from the if you are at k, then k minus 1, that is your previous state estimate. Then the actual measurement, for example current and voltage, whatever parameters is there, then we will, so it means the estimated state at time step k then is equals to the previous one plus what, plus the this formula where k is Kelvin gain, we that is a factor, and then the yk actual measurement, yk is this is the actual measurement that is there for that instant. I'm not talking about instant of time, instant of anything. Yk minus h xk minus 1, that h is the measurement matrix. It means what we are doing here in the smart grid, that if you have an estimated state, you have to find out the state of that particular estimated state at time k. It means you have to take care of previous state estimate, then the actual measurement, current or whatever, that is the actual measurement, and but from that actual measurement we have to subtract the measurement matrix of the previous one, okay, minus 1. So then, and we have to take care of the Kelvin gain. So this would be the estimated state at time step. Okay, now here in case of our network for the space, if we go up, you say this is the equation: yk is equal to f of the physics xk plus epsilon of k. Excuse me. So in this case, yk, I mentioned it here again, the equation where yk is the predicted sensor output using physics informed module, because as I said, we already modeled a physics informed network with, then now our predicted sensor output from that yk equals will be a predicted sensor output using physics informed module, whereas the sensor noise or bias corrected during estimation, because we are doing an estimation and we are correcting that. This means sensor noise or bias that we corrected during estimation, we have to add that into it. So the model is trained on expected equipment behavior. It means this would be our sensor physics integration. Now, the features in the smart grid and the NASA spacecraft, if we talk about the sensor types, we have PMUs and se- current transformers, smart meters, and these are some of the things that we have over there. Whereas in case of all others, we have uh, some of the more parameters that we discuss in the smart grid. One is the filtering technique. We use Kalman filtering. Whereas for the NASA, neural prediction with physics models. Whereas for the key equation, these are the two key equations that I just mentioned for the smart grid and for the NASA. So the challenge, what challenge has been addressed for the smart grid, noise and latency and the drift. For the NASA, it will take care of radiation, thermal variation, and real-time delay. And for the output feature, output usage, input to MPC and pin updates. So that is in the smart grid. Whereas the output feature for the NASA spacecraft is subsystem decision and energy safety validation. So let's do a comparative study here. Meanwhile, I'm trying to keep the video running. Sometime it goes off because I'm concentrating more on these slides, and sometimes I'm not able to see because I have to view it bigger. And now we are talking about the components in smart grid, and in the NASA smart grid is A and NASA is B. So for the physics-informed neural network estimator that learns in the smart grid physics, Ohm's, Kirchhoff's laws, and just voltage and current readings. Whereas here in NASA's that learns equipment thermal electrical response based on the mission. But then for the noise filtering, for the hybrid data fusion, for MPC feedback use, and the key challenges I addressed here, the buffered and input windows for the smart grid, the buffered input window stores PMU or the smart meter data in short window to mitigate SCADA latency, because later on we have to let it go for this SCADA, right? So we are talking about the buffer input window. Whereas for the NASA's spacecraft, buffers thermal voltage and the IMU data to smooth space induced fluctuation, because some fluctuations are induced in the space. So the data that is to the space induced fluctuations. So now for the noise filtering, Kalman filter equations for voltage and current noise we use, and for the spacecraft AI based denoising equation that I explained before to components for radiation induced sensors noise. For the hybrid data and fusion in the space, in the smart grid combines live sensor input plus the pin physics uh, prediction for the reliable state. Now, when I keep saying that we are talking about the losses, total loss is the loss of the physics informed neural network, and the losses of the actual data, and the losses in the in the boundary. When I talk about boundary in deep neural network, it means the more the loss it means I'm away from the predicted value. So in order to be close to the predicted value, I have to somehow set my system to minimize these losses. So in first is to calculate those losses. First is to generate the predicted or the desired outputs related to the physics, related to the data, and related to the boundary. Boundary is also very important in this model, because we cannot let the model go to, I cannot say that model is for everything. It has to be within certain boundaries. Let's say boundaries of certain boundaries of the voltage. Let's say it will operate between, say, 10 volts to 100 volts, say for example. And we have to make sure that it is actual with the physics informed neural network as well, and it takes care of the specified material of the generators, motors, electronic circuits, devices, components, and it is within the physics, and it obeys the physics laws. Then the actual data, whatever is being sensed, because in real time we have no control, though we can control later on, but we have no control. So we have to make sure that how far we are from the predicted values. So if we calculate the losses and we try to minimize the losses, we can be as close as possible to the predicted or the desired results. So once we are done, we talk about the MPC feedback use. So this thing feeds to MPC for safe switching for the smart grid, load shedding and reactive power balancing. That there has to be something that has to be fed back, right? In case of space, feeds XK I mentioned over there, right? It feeds XK. So what is the XK? If we go back here and you see the equations, these are the two equations, right? So here here it is. So in this case, xk is the estimated state at time step k in the smart grid. It means if this has been fed back to for proper to take care of or to actuate some of the systems, that xk estimated state at time step k has to be determined, like this has to be fed. Whereas in the space, the sensor noise or bias corrected during estimation. So in this case, we talk about predicted YK. I'm talking about YK. I'm sorry, talking about YK. Predicted sensors output using physics informed network. One, how we compare for the smart grid, we are talking about estimated state at time step k of that of the smart grid, whereas in the physics informed neural network for the spacecraft, we are talking about yk, where that is the predicted sensor output using physics informed. So these are the two differences. So this has to be fed back, and then the key challenge addressed here is in the smart grid is harmonics, load variability, and communication delay. Whereas in the NASA's, we talk about SUs, thermal cycles, signals lost during eclipse. So for the step number 7, boundary conditions encoding in our model, smart grid, node substations and boundary surfaces. I think for from next step 7 to onward, we will move on to the next video presentations in another video because too long. So thanks for your time and being with me. Keep watching. Thank you.